ARBURG had the idea of a custom, medical-grade, reusable face mask, and by marshaling their internal resources, they rocketed the idea through design, prototyping, and production, all in just 41 days. During the next 30 minutes, I'll share how this was done and what lessons we learned along the way that we believe that an organization can be applied to. I'll give you a quick spoiler alert. It's all about prototyping workflow and using the correct materials. Before I start the story, I'll take a quick moment to introduce myself. Lucas, I appreciate the warm words. As part of the ARBURG additive team, I head up the sales and marketing efforts here in the US for the Freeformer. I've spent well over a decade in the additive industry, watching 3D printing expand from more or less an unknown technology to a widely adopted solution for prototyping and manufacturing. It's been an exciting ride, and I love to see a feel-good story like this, where 3D printing was able to step up and aid a good cause. So let's talk a little bit about the project. The project started with two different parallel requests. The first request came from an employee at the hospital in Rottweil, Germany. That hospital employee remembered seeing ARBURG's booth at the K Show in 2019. For those of you not familiar with it, the K Show is a trade show known as the world's premier fair for plastics and rubber industry. It takes place every 3 years in Düsseldorf, Germany. It's similar to the NPE show in the US. At that show back in 2019, ARBURG displayed a molding system making UVEX protective glasses right in their booth. So the hospital employee contacted ARBURG and explained how those glasses could be used as PPE if ARBURG could supply them in a clear format. ARBURG saw this as an ideal opportunity to assist a local hospital. Luckily, the mold from UVEX was still available, and our partners had quick access to the correct material. ARBURG set up a system devoted to producing clear glasses and kicked off a production run. We took pride in the ability to offer assistance to surrounding hospitals and delivered all the supplies at no cost. The first delivery of 1,200 units was on April 24th, only 25 days from the original request. In parallel to that, a second request came from one of the managing directors at ARBURG Germany. He was concerned about the availability of masks for his employees in the midst of the crisis. As I'm sure everyone remembers, PPE such as masks, gloves, and face shields, normally available to anyone and easily obtained, were all diverted to healthcare organizations to assist in the pandemic. The director asked ARBURG's additive group to design and print some face masks for employees to wear at internal meetings in the office. The additive group took the challenge and ran with it. The first mask concept was to cover and divert. The design essentially covered the face and directed exhaled air down and away, thus trapping any moisture particles in their clothing. This design protected the wearer from any aerosol particles coming towards them, and then protected anyone around them from aerosol particles exhaled by the user. It was a simple and effective design. ARBURG's additive group has the tools to quickly turn the idea into a part. Several were printed and delivered to management, who used the masks when hosting meetings in the conference rooms. So before we showcase the mask design, let's take a quick look at the tool. Lucas's team gave you a quick overview of the ARBURG Prototyping Center, which you saw in his video. We call it the APC. So let me give you a quick look at the system underneath the hood. What makes the Freeformer an ideal tool for prototyping face masks is the ability to run any granulate material through the system once it's been tuned for it. The material is loaded into the hoppers you can see on the top right, and then processed through a screw and barrel. Lastly, the material is extruded through a nozzle as a string of micro droplets. This processing method and ARBURG's custom printing software give the user full control of the system. Users can choose to print parts or sections of parts in varying densities, from fully dense and similar to a molded part, to a low density, creating a lightweight and sometimes flexible part. Here's a great example of that. As you can see, we have a fuller density on the surrounding border and a nice light density in the middle. Although it's real thermoplastic, so it's still very durable. With this level of flexibility, the team could use medical grade materials to print face masks that could be used without any danger to the wearer. No post-processing or coating of the parts is needed to make them safe. And here we see the first mask concept. Very simple concept, as we mentioned, diverting the air down and away. It was designed and printed on March 26th, just a few days before the glasses project kicked off. The first design was printed on the freeformer in a flexible Shore 70A TPU, or thermoplastic polyurethane material. This flexible material was a medical grade. So here's an example of a material that can give you the idea of flexibility, durability, and resilience in a printed part. Here you see a piece made out of that material. You can see it's a nice thin section and very durable, stretchy, and as I mentioned, comes in a medical grade. The speed at which this idea became a fully functional part being used in the conference rooms was an immediate success. So much so that those involved wonder if they could do more. What's stopping ARBURG from designing and producing a fully functional PPE mask using the resources the company has available? ARBURG can quickly create prototypes with their fleet of freeformers, and they're moving to mass production with their molding systems. The bottom line, nothing is stopping us from stepping up and helping with the PPE shortage. Well, where to start? So first, we needed a design for the mask. One best practice is to keep the KISS principle in mind when attacking these challenges. That's KISS with 2 S's. It's an acronym for keep it simple, stupid. A design principle noted by the US Navy in the 1960s. With that in mind, we looked at all the available mask types on the market and noted the pros and cons of each mask to help guide our design. So first we looked at disposable masks. Disposable masks are simple, inexpensive, and can be purchased in bulk. They're an easy solution, but they're designed to be thrown away after a single use. And this design creates a lot of waste and clashes with ARBURG's commitment to environmental sustainability. Next, we looked at the fabric masks. These are relatively inexpensive and better for the environment since they can be washed and reused. However, a single person will need to have multiple masks since they really should be washed daily. There's also a debate now about what kind of fabric is the best and how effective they really are. Next, we looked at the full face mask. These are the types of masks that you'd see maybe a firefighter wearing to a burning building. We thought that these would be a little bit overkill for the general public. Plus, if you wanted to try one during the pandemic, it would be impossible to procure since these were all diverted to medical workers. So lastly, we looked at the common half respirator. It's a good design, it's got replaceable filters, and it can be sterilized quickly. However, these two tend to be on the expensive side. So before we get to our choice, let's get the audience to weigh in. Which one of these masks do our listeners prefer? So let's go ahead to our first question. Here we see, what mask do you prefer? Disposable, fabric, full face, or half respirator? So we'll give it a few seconds while the audience chimes in. All right.
That's right. It looks like the fabric mask is preferred.
Yeah, you know.
Next to disposable and a half resp.
Excellent. All right. So it looks like the fabric mask definitely won, and disposable and half respirator almost have a tie there. All right. Excellent. Well, ARBURG decided to take the common half respirator design and build on it. We wanted to make a simplistic yet functional PPE mask of our own. So taking the common half respirator as a base for our design, we started by laying out our design goals and criteria. First, cost. We immediately threw cost out the window. We didn't want concerns about cost to be impacted with this design, mostly because we were going to donate all of these masks that we were producing, so cost wasn't really a point for us. Next, we looked at sizing. So in an ideal world, a one-size-fits-all mask would be preferred. It's easier to manufacture, and it's easier for users not to have to choose what size might fit their face. If more than one size is needed, we'll need to make sure it's simple for users to decide which version is right for them. Next, we looked at sterilization. The mask needs to be sterilizable. In an effort not to create more waste, we wanted to make sure that it was simply sterilizable. We looked at designing around 2 different platforms for sterilization. For the general public, sterilizing using alcohol wipes would probably be the best because they're pretty commonly available. For our professional users, maybe in a hospital setting, a hospital-grade sterilization would be necessary. Now, this adds in some additional constraints, mainly around temperature. Let's say if the users wanted to use an autoclave. Then we moved on to standardization. Standardization, at least I feel, is always a good point when designing something. So we looked at all of the different connections on the mask, and we wanted them to be standardized, the goal being that the mask would be compatible with commonly available filters or maybe respirators. With standard connections, the mask would be able to adapt to the user's needs as they change. And then lastly, flexibility. We wanted it to be able to function without filters, mimicking the original concept in the scenario where maybe filters aren't available and we couldn't get them. The mask can still be used and keep the wearers and around them safe. So with that in mind, and ARBURG being a machine designer and producer, we have a team of system designers. So we leaned on that group to design a mask that fit the criteria that we laid out. The results? The designers split the mask into 3 separate parts. This was for ease of manufacturing and ease of cleaning. Each part had their own function. Let's look at it from left to right. So on the left-hand side, we have a soft, flexible piece that will come in contact with the user's face. This piece we nicknamed the LSR mask. In the middle, we have a rigid frame that will hold the mask tight to the user's face and also act as a support structure for the flexible LSR mask. We called this the Smart Shield. And then lastly, we had a filter and exhaust valve that would do exactly what their names suggest. They'd filter the incoming air, exhaust the outgoing air. Now, we wanted to create our own filter because even though the connections were going to be standard and they could accommodate any commonly available filters during the pandemic, these filters just were not commonly available. So we wanted to offer a full package to our wearers. Once the design was created by the design team, they sent the CAD over to the additive team to create prototypes for testing. The additive team started with the LSR mask section of the design. They looked at the size of the mask and first thought people may have different size faces. For an example, I know you can't see me because I'm sitting, but when I'm standing, I'm about 6'4" tall. So it's a fair assumption for me to believe that my face at 6'4" might be a little bit different than, let's say, my wife's at 5'4", since there's a foot difference in height. Do we need different masks? What about the different facial structures between males and females? Do we maybe need different masks to accommodate males and females? Second, we looked at the material, the flexibility and the softness. The mask needs to be strong enough to retain its shape, but soft enough against the face to be comfortable and worn all day long. Ideally, we want to find a single material that will work for both of these criteria. Liquid silicone rubber, also known as LSR, is a common medical material used with face masks. It's durable at high temperatures, easy to sterilize with alcohol wipes or hospital-grade sterilization. Plus, it's soft and it molds nicely to the face, ensuring there's no air gaps. That would be the ideal material. So with that material in mind for production, we set off to test some different shapes and how soft the material could get before it no longer held its shape. So the additive team started by printing out several different versions of the LSR mask. They printed several sizes and asked male and female employees around the office to try them on. The outcome was that one medium version hit the sweet spot and that fit everyone pretty well. To test material softness, the group tried out a single material version and then a multi-material version. As you can see on the screen, the multi-material version is the white with the off-white, and the single material version is that clearish. So the concern was that the filter may sag and flop around if the material is too soft. The team tried a single material version using a medical grade Shore 30 TPE, and then a multi-material version using the same TPE, but combining it with a PC ABS. Once we had several versions printed out, we combined those with some prototypes of the Smart Shield, and the frame of the Smart Shield held the single material version quite well to the face. The single material version performed great. And that made it easier because that was going to be easier for us to manufacture as well. Lastly, the team printed several models in varying softness and performed the same trials as they did with the different size masks. This helped them zero in on the best Shore value for softness for the LSR that was to be used in production. So with all this talk of materials, we're interested to hear from the audience. What types of materials do you guys usually use? So here comes question 2. How many materials do you typically design your parts in? Do you design in single materials, dual material of 2 components, more than 2 materials, or maybe you're not quite sure? So we'll give a few minutes for that question as everybody clicks an answer. Okay, looks like single material is the winner, with dual material or 2 component parts pretty close behind. All right, thank you. So let's move on to part 2. So in tandem with the prototyping of the LSR mask, the team started working on the frame that supports it, the Smart Shield. This section wraps around the LSR mask and holds it tight to the face. It also acts as the frame that supports the filter. So some design constraints that the team had to think about. They needed first to choose a material, and that was a material to prototype it. So the part needs to be rigid enough to hold the mask and rigid enough to connect the filter. However, it needs to be flexible enough to bend around the mask and also flexible enough not to break or crack when putting it on the face or removing it from the face. Plus, one last design item. As you can see on the right there, there's a snap cover that covers the filter connection. This has a snap and also a living hinge on it. So those were 2 other things that needed to be thought of when choosing a material. So with those constraints laid out, the team agreed that polypropylene was the best material to start in. It catered well to those snap fits, the living hinges on the cover. It would flex nicely around the LSR mask, and there's also medical grades of the material. So it could be sterilized and testers can wear it on their face without worrying about the materials. So the team printed several iterations of the mask and along the way made small adjustments in the snaps and hinges to assure longevity of the device. The polypropylene ended up working so well for the prototyping, it was chosen to be the final production material as well. And lastly, onto the filter and exhaust valve. The mask was designed to be used with commonly available filters from suppliers such as 3M or Honeywell. But during the height of the crisis, these filters just were not available to the general public. So ARBURG wanted to design and produce one of their own. The design criteria for the filter and the exhaust valve were very straightforward. Standard connections, a built-in air valve, a built-in exhaust valve. Really, shape and size are the only open question. So the team started with a simple and generic round filter housing. Once the part was printed and assembled, it was quickly clear that the filter was too large. When tested on the mask, it limited the forward visibility of the wearer. They couldn't quite see straight, and that was a problem. So the filter needed to be smaller. The team scaled down the size and reprinted. The visibility problem was solved, but we created a new problem. This smaller version didn't have enough surface area for the air to be drawn in over the filter. This design notably limited the amount of air the wearer could draw in, and it caused shortness of breath. Got to be a better solution. Well, what about a larger filter, but maybe with a different shape? A few concepts were drawn up, quickly printed out, and tested. The winner was a triangular shape. It ended up being just as large as the first design, but we cut out the contouring of the top edges right in this area here. So visibility was increased and we solved that problem. Also, there was enough surface area for the air to be drawn in and the user could easily breathe. The group decided they would prototype in PCABS because the material performed well with the thin walls of the filter design, the snaps of the cover, and also it was available in a medical grade. So again, safe testing. Finally, the exhaust valve. Now this was the heart of the filter, although an extraordinarily simple design. But here is where the team saw that by prototyping this, they had the opportunity to assist the production group. The production group wanted to use sonic welding to assemble the exhaust valve with the fabric filter. PCABS was chosen for the prototyping the exhaust valve so that it was compatible with the sonic welding process. The production group could then use the prototypes to hone in their process prior to production. That gave them a head start on setting up their manufacturing line. So we've discussed many types of material up to this point that were used in prototyping. TPUs and TPEs, PCABS, and polypropylene. So for our final question to the audience, we're interested to hear what types of materials do you like to use in your products? So on to question 3. What material are you currently using? ABS, PCABS, polypropylene, PC, PA or nylon, TPE, TPU, some high temp materials, or others. And feel free to choose as many as you use. So we'll give that a few seconds. All right, and oh, look at that, polypropylene, a pretty clear winner. And then runners up, we have ABS, PCABS, TPEs and TPUs. Excellent, okay. A couple of high temp users there, wonderful. All right, so let's move on. So let's talk a little bit about the production group. In parallel to design and prototyping, the production team was hard at work getting their portion of the process ready. Now, it took just a month to go from an idea to cutting molds. The LSR mask portion was the most complicated out of the three. And this was due to the complexity of molding liquid silicone rubber. Because of the low viscosity of LSR, during the injection process, the possibility of trapped air bubbles is extraordinarily high. However, this can be avoided by focusing on three key areas: part design, the gauging points, and the mold design. With a good simulation software, all of these details can be worked out ahead of production. And with such a compressed timeline, ARBURG relied heavily on simulation software for our mask and mold design. This simulation was done in parallel to the prototyping. So here you can see the final product with three sections separated out and then the final packaging. In the final packaging, we added a flyer with a story behind the mask and a thank you to our partners who helped make this a reality. So if you can see in my video, here is the actual mask. You can see it separates into two pieces for ease of cleaning. Here's our LSR portion. Here's our Smart Shield. You'll notice that we have elastic bands to hold it tight to the face, and the parts snap back in together nicely. Here is also our cover and our filter connection. Notice the living hinges and the snap fit. Pretty cool design, works quite well. So I mentioned partners. Speaking of partners, ARBURG specializes in the manufacturing of the molding equipment, but relies on the partners for all the other pieces of the process, such as materials or mold design. For an example, our partner FOBA supplied the machined mold for the Smart Shield, and our partner Borealis supplied the polypropylene that the Smart Shield was molded from. Here's a complete list of our partners that donated time and resources to the project. And as always, we want to thank them for their roles. So to help convey the speed at which the different phases were completed, here's a timeline of the project. I'll run through it quickly with you. The project started on the 23rd of March. This was the design of the mask and the prototyping of that design along with the simulation of the final design. Just a month later, on April 24th, the LSR mold was manufactured by one of ARBURG's partners. A few days later, a partner started on manufacturing the mold for the Smart Shield. And 41 days later, on May 2nd, the project was kicked off. 2 molding machines were set up and started running the same day. We concentrated on the first 2 pieces since together, they created that fully functional mask. A little bit later on June 16th, the filter housing production started. And finally, a shot of the production cell. These are the machines that were set up and started running the parts in a matter of hours. The system in the background is running the glasses. So if you remember from the beginning, the glasses were done in tandem to this project. We received a mold from UVEX. It was a single cavity mold with a cycle time of 45 seconds. So with that set up in the background, we can produce up to 2,000 glasses every day. The system in the foreground is running the mass production. We used a 4-cavity mold with a cycle time of 50 seconds. And with this setup, we can output roughly 6,500 pieces a day. The picture on the right-hand side shows the masks in the hand of the gripper, cooling down before moving to the next phase. So, what I would like to show you next is a 2-minute video that shows the actual process of how it's being done. Ooh. Let's see if I can get this to play. my mistake. I think we left off right here. Excellent. So with that video, we got to see how the actual process worked. So in conclusion, there were a few lessons that I hope stood out during this story. Number one, get involved. If you have the resources to help, please do. Those in need will be ever grateful. Number two, all hands on deck. At ARBURG, everyone stepped up to play a part to make this vision a reality. It's that teamwork that gets things done. And then third, amazing things can be done in record timelines with the right tools. From concept to production in 41 days is a fast design cycle, but it's possible with the right teamwork and the correct tools. Hopefully the lessons we learned are ones that you can implement in your organization to help you be just as successful with your products. Bring flexibility to your prototyping. Use it more than just for concept models. Use the correct materials. When prototyping, use materials that are the same or close to your production materials. Don't sacrifice on materials. Use a prototype to test not only your fit and form, but also your function. And then lastly, test your manufacturing process during your prototyping phase. Let your prototype help both the engineering team and the manufacturing teams. And above all, don't limit what a functional prototype can do for your organization. Thank you for joining us, and we hope you enjoyed our story. I believe at this time we're going to move to a quick survey and take some questions from the audience. I see we have quite a few in the Q&A section so far.
All right, thank you, Jerry. Look, as you said, we have several questions going on. Let me just start off with, were the prototyping materials medical grade?
Oh, great question. Yes, so when we chose to do our prototyping, we chose materials that were not only good for the function, but also we wanted all the materials to be medical grade materials, simply because we wanted people around the office to be able to try on the parts, wear them, give us feedback, but not to have any concern about the materials. So we did want to use medical grade materials.
Excellent. This question a little bit more about the design of the mask. You went over the filter and the valve for intake. Now, was there any protection against the exhalation, so that when the user would breathe it out, was that filtered at all?
Oh yeah, excellent question. So are we referring to with the filter assembled on or without the filter on? I guess I can speak to both. So
yeah, I think the question was against, since as with COVID, the primary protection of wearing a mask is actually to protect others from your exhales, your exhalation. So if you could detail a little bit better how the mask will protect against that.
Sure.
Will filter out what you're exhaling.
Yeah, so from the filter design that I saw, there is a filter as you're drawing in, and also as the exhale comes out. I do believe that there is a certain section of the filter that it goes through. I think it also aims the air down, right? So to put that air at least away from the people you're talking to.
All right. Now, start off with how many masks were produced and donated?
So in total, I think we crested just over 10,000 masks that were donated to the local region around Mossberg.
And what was the customer feedback?
Oh, that's a great question. So some of the feedback we got from our partners who we donated to, from some of the local areas we donated to. I think feedback on the mask design itself, they were quite happy with the design. It seemed to fit quite well. The masks were very comfortable over a long period of time. As you can see, from the softness here, it was a very comfortable, soft-fitting mask. Also, I think they were very happy with the speed at which we were able to deliver.
Now, are these masks available for purchase?
These are not. Actually, we donated the full run of our masks. Everything was given away at no cost, and then we moved those systems on to different applications.
Yeah, Jerry, maybe I can quickly interrupt here. Thank you. First of all, thank you for the presentation. And no, they are not available to purchase these masks because this was a one-time charity event for us. So we are not a producer of medical products. That we are a machine builder, machine manufacturer, and our customers are producing masks, and this is the philosophy of ARBURG. We don't want to be competitor of our customer. Same in additive, like in injection molding. So definitely you can probably buy the whole project here, the whole mask project set up here at ARBURG, but we don't want to, we just don't want to be a competitor of our customers. So also in additive manufacturing, we are having here our ARBURG prototyping center, and we are not selling parts or making rapid prototyping or something, because we have customers who are offering that kind of service, and this is their business. We are producing the machines to do it, and we are showing here in our application centers, in our technology centers, what is possible, but the business needs to be done by our customers.
Great, thanks, Luke.
So I think that will also address another question, was all the tooling donated? I believe we're keeping the tooling in-house currently, and this project was more as something to address an immediate need and to kind of demonstrate kind of the capabilities of ARBURG and our partners. Here's another one kind of related to the R&D. Is at what stage of the project were the mold makers involved?
Oh, great question. I think if we were to look back at the timeline here, what we can see is where the project started in March and the mold cutting started towards the end of April. Lucas, if you recall as well, I want to say we had our partners involved probably by early April.
I know that our mold makers were even working on public holidays on Sundays to realize this project. So, but yeah, directly from, I think week 3 or 4, Jerry, I think we involved directly the mold makers here. And yeah, and they supported us also in the whole process.
Great.
So, and just while we're talking on the mold design and the tooling, just a quick question, if we have an answer for it. Did the LSR process need a tempering procedure? I'm not super familiar with LSR molding, so.
So that's a little past my experience on the project.
Yeah.
Also past my experience, we can definitely give an answer. We will ask our specialists here,
yeah.
and we can give an answer later on.
Yeah, sure.
Yeah, sorry, Erhard, we'll have to follow up with you on that one to get you an answer there. Can we go over a little bit kind of how our APF process and FDM are different from each other?
Sure, happy to. In fact, if I can jump back to our under the hood look, I would be happy to show the difference. So a couple of main differences you'll look at when you look at ARBURG's technology versus traditional FDM or FFF. And what you will see, let's see, I can grab, here we go. So of course, starting up here in the hopper, we're using a different substrate. So starting with pellets instead of filament. One thing to point out there is the majority of the filament that FDM or FFF uses, that filament is not what we like to call neat material, right? That's not just the organic material. There's often a lot of fillers in that material to help it essentially 3D print, right, for the process. So we're using clean, neat, original material. We're putting that through a screw and barrel, which is heating it up. And then we are pushing it into our nozzle assembly here. And again, one of the main differences you're going to see is even though we do use the similar toolpath method, right, of tracing down and building up layers, what we're tracing down is not actually a round filament. We're putting down a string of micro droplets. And the advantage of the micro droplets is that they seat very nicely one layer into the next. So we don't have that same, what I'll call a log cabin effect of the air gaps between layers that you often see in FDM. So you're getting a higher density with this process. Hopefully that answers the question. Well, one other thing I will mention that is just interesting to note. So with the FDM or the FFF process, those of you who have had experience with it, you'll know that it's somewhat difficult to print flexible materials because you're often pushing a rope, essentially. With this process, because of the pressure here in this area pushing the material through, we've had a lot of success printing flexible and ultra flexible materials. This being, let's say, a Shore 30A material that was printed. Hopefully that answers the question.
I think that was in quite sufficient detail. And a kind of a follow-up to that, how does the surface quality between the freeform process and the filament compare?
Oh yeah, great question. Well, the surface finish, as we all know, if we're familiar with additive, is going to be relative to a few items, right? So you're going to look at material, you're going to look at filament or droplet size, i.e. layer size, and you're going to look at how those two interact together and the material lays down. There's also a question of support interaction, but from what we've seen, and I'll say across a very general and broad term, because surface quality will change per material, and one of the advantages of the freeformer is to be able to print out an extraordinarily wide variety of materials, some materials that you'll never see in FDM. So we can't really compare surface finish. But let's say you took generic ABS. We're printing at about a 0.2 millimeter layer thickness out of our nozzle, or about a 4 thousandths. So if you're comparing that to, say, FDM printing in a 5 thou layer, because they're micro droplets, you're going to see a little bit nicer surface finish out of the ARBURG than you are going to be on the freeformer. That trade-off, of course, is that the freeformer, it's going to take a touch longer for that print because you're laying down more material in smaller droplets and layer sizes. So that's a little bit of your trade-off.
Now, a couple questions more on the prototyping and design process here. How does the production from a prototype of the freeformer differ in contrast to the mass production of an all-rounder in regards to product composition? So I guess it's a question more on the quality difference between the part off the freeformer than it is in the final production off of the all-rounder.
So I suppose we could probably attack that question from a few different angles, right? So if you're talking about part quality, you know, for instance, the freeformer can't quite print silicone. So it's very hard for us to compare, let's say, this soft, flexible silicone piece to one that would have been made out of this material. Even though they're similar shore values, the two materials are going to feel very different. If you're looking at, you know, a surface finish aspect, of course, your surface finish on a mold is going to be better than any additive process, right? Hence, additive always trying to keep up with molding. If you're looking at strength-wise, so let's take our Smart Shield, for instance. When printed in polypropylene versus when molded in polypropylene, if you're looking at the strength of the parts, because of the process that you're going to find with the ARBURG, the laying down of those micro droplets, the density it's able to achieve, you're actually going to find a very similar, it is not exactly the same, but a very similar part printed strength-wise to a molded part. Hopefully that helps answer the question.
I think it was fairly detailed. So, and just a general process question: were these parts produced with support like other AM processes like FDM? Yeah.
So if support is necessary, we need to use support just like, say, an FDM part would, or most of the industry. Where we can design for additive and we can design around using support, we'll certainly do that. That speeds up the process. Of course, the simplicity of support removal is easier. When support is needed, we like to use, we have a few different support materials available, but we like to use a water-soluble support that dissolves right out with warm water. Makes the process a little bit easier for us. Also makes it clean without having to add additional chemicals.
And so this is more of a general question on the design process and how this got initialized. How did you determine the unmet customer needs, and did you use a specific innovation process?
Oh, to determine the customer needs. That's a great question. So I think as we went through the design process, and I tried to detail some of that in the presentation, a lot of it was around the prototyping group, the design group, input from the managing director and some of the people who use that original black mask in the meetings. Thoughts around, you know, look at that design criteria of when we create a mask, you know, what does it need to have? You know, obviously the sterilizability, those things weren't obvious to us, but others were things that, you know, comfort, just trying not to reinvent the wheel, use designs that were already out there. Remember, we think of that KISS design process where you don't want to overcomplicate something. So Lucas, unless you know of anything that I may have missed there, I would say there wasn't really a formal process we used, especially on such a compressed timeline. We were just trying to come out with the best standardized mask design we could and do it as quick as possible.
Yeah, Jerry, you nailed it. I mean, the compressed time we had, and we just looked what's available in the market, what the standards is. We cannot reinvent the wheel. We are no producer of mask or something. So we just wanted to give a solution as quick as possible. That was the goal.
Right, and that really drove the speed, as well as, you know, one of the things that I tried to emphasize during the presentation, which is prototyping with the right materials. Right, if you use ABS to prototype for everything, you're not really able to test your designs to the effect that you would want to. So by using the right materials, and in most cases the production materials for the prototyping, we could really do the type of testing that helped ensure a certain level of confidence that when we got to production, we've chosen the right materials, we've chosen the right design, and it's going to come out and it's going to perform in the intended way.
Yeah, I just wanted to kind of remind the context here is, you know, this was back in March of last year, which I don't know, feels like 1,000 years ago. It was a lot going on, a lot of questions, and it was a very clear need for medical supplies, mask supplies. So everybody was trying to figure out how we can help. Not just ARBURG, everybody was, and we saw kind of the clearest and simplest way forward for us was to try and produce these masks as quickly as possible, and that's kind of a unique thing that ARBURG and our partners could do in a very short period of time, back in March and April of last year. One last question coming up. How quick is the APF process compared to other AM processes?
Yeah, I'd be happy to jump on that. So as I had mentioned when comparing and contrasting the FDM versus the APF process, what you're going to see is that the APF process, in the manner in which it's laying down droplets, it's going to be similar to an FDM process printing at, let's say, the same layer thickness, right? So that 4,000th or 0.2 millimeters. It's certainly not going to be as fast as, say, something like an HP process, right? Where you're printing into a powder bed, you don't have to put down support material. You know, some of the resin processes that are extraordinarily fast. What you're going to see here is going to be a little bit slower than that. Like I said, comparable to FDM. The advantage being that you're using actual thermoplastics. I like to make the comparison, and you know, this fits for some prototyping. If you're going to print a part overnight, then the difference between, say, 6 hours or 10 hours doesn't really matter, because you're not going to get that part until you show up the next day.
How big was the benefit? Sorry.
Oh,
yep,
sorry. There was a question directly from the beginning. Maybe you can come up with that, with the filter and the exhaust valve. So there was, I think it was Clement.
We mentioned at the beginning. I don't know if you had any extra input there about how the air is filtered on the inhale and the exhale. Because as we all know, with COVID, what's really critical to be filtered is what you are exhaling, which is the real purpose of these filters.
Yeah. So at the beginning, in one of the first prototypes, one of the first slides in Jerry's presentation was seen, there was an exhaust valve. But later on in the slides, you could see that we didn't use the valve anymore, and we had just the filter, which was filtering the incoming and the outcoming air. So we didn't have the certification, but we had the same standard like an FFP2 mask. I hope that answers that question.
Yeah, no, that's great. Thank you, Lucas.
All right, thanks. I think that brings us just about up to time. Thanks all for attending and your great questions. If I give the chance to Jerry and Lucas here, if any last comments.
Yeah, one thing I will mention is we actually created a wonderful case study out of this that we're in the midst of publishing. So those of you who attended the webinar, first off, I want to thank you. Second of all, I will make sure that everyone gets a copy of that case study once it's published.
Yeah, I also want to say thank you from our side here. I just want to mention, if you guys are interested in our freeformer technology, you can contact us. We've shown just quickly here our prototyping center where we print benchmarks. If you want to see how your part is looking out of the freeformer, send us the file, get in contact with us, and then you can have freeformer parts in hand. So thank you very much for attending, and it was nice having that webinar. And thank you, Jerry, for that nice presentation, and thank you also, Tom.
Yeah. Thanks, everyone, and have a good rest of your day.
Thank you.